Living in the Bay Area, we're used to change. Fog in the morning, sun by afternoon, and maybe a different forecast just a few miles away. But if we step back from the day-to-day shifts, a larger pattern starts to emerge. That pattern, the rhythm of wet winters and dry summers, of cool coasts and warm inland valleys, is what we call climate. Understanding where that rhythm comes from begins with looking at what shapes it. In this video, we'll talk about the phenomena that control climate, and then what those climate patterns look like. To talk about climate, we have to begin with weather, which was the subject of our last module. So if weather is the atmospheric conditions at a specific time and place, like sun today and rain tomorrow in San Bruno, then climate is the long-term average of weather patterns. Meteorologists or weather scientists look at records of weather and figure out what the pattern was, usually over a span of 30 years, and then they determine what it looks like generally. So we could say, for example, there are usually warm, dry summers in San Bruno, even if we get a little rain here and there. As with everything else in geography, climate is a system, and all four spheres play a part, some more obviously than others. Our atmosphere, with the gases in the air and atmospheric circulation, form a sort of space for climate to happen. And the hydrosphere, with moisture and precipitation, also plays a big role, both because humidity is half of the equation, but also because it has a moderating effect on temperature, as we'll see shortly. These two are the heavy hitters of climate, but the lithosphere also has its part through topography or hilliness, affecting the movement of moisture. And of course, when we get into climate change in the next video, we'll see in more depth how the lithosphere and the biosphere participate in the carbon cycle, which humans are now changing, along with the planet's climate. So now let's talk about the natural phenomena that control or produce climate. This will help us connect some dots from what we've learned in the past few modules to climate as a whole. So the first most basic control of climate is, of course, latitude. You should recall from the Earth-Sun relationship that the tilt of the Earth affects how directly the sun's energy hits the surface. So at a lower latitude, you're getting more heat near the equator, and then at a higher latitude, you're getting less heat near the poles. That pattern holds up fairly clearly on this map here, with high temp in red near the equator and low temp in blue near the poles. Of course, you might notice some blue on the interior of Asia and a little bit in the Americas. Those are mountain ranges. So elevation controls climate through what is called the lapse rate, which is this average rate of temperature change that we see where the temperature will decrease by about 3.5 degrees Fahrenheit for every 1,000 feet you go up in elevation. We can see this effect by comparing temperature patterns from sites at different elevations. And we do this by looking at average daily mean temperatures, which is a way of saying the pattern of those middle temperatures of days throughout the year. So not the highest point of the day and not the lowest point, but the average between, the mean. So here we have two sites in Bolivia in South America. Concepcion to the east is at 1,600 feet above sea level, while La Paz to the west is at over 13,000 feet above sea level, so like over 2 miles above. And we can see that they have roughly the same temperature pattern, but Concepcion, the lower of the two, is usually like 30 degrees warmer. In addition to topography affecting temperature through elevation, it also affects moisture by creating what are called rain shadows. As moist air rises up a hill or a mountain slope, it cools and precipitates, leaving the air drier on the other side. We can see this clearly as a pattern of drier climate on the eastern side of mountain ranges in the continental US because our prevailing winds come from the west. So, this is especially obvious in the Pacific Northwest, where the Olympic Mountains and the Cascade Range follow along the coast. In the map here, we can see the western sides of those mountain ranges in dark blue, and a ton of precipitation is just being dumped from the oceanic air as it travels over these mountains. Seattle, Washington is between the ranges, so it still gets a lot of rain, but Spokane is to the east of both ranges and gets relatively little precipitation. It's a difference of about 20 inches over the average year. Continentality, or the distance from the ocean, is a big reason that climates differ between coastal and inland places. Oceans moderate temperature extremes because water and land heat and cool in very different ways. So land heats up faster and reaches higher temperatures than water, but it also loses that heat more quickly. Water, on the other hand, moves the heat around through currents, and evaporation also cools the surface. So coastal areas like Vancouver stay mild year-round, while inland cities like Winnipeg, at nearly the same latitude, swing between hot summers and very cold winters. So that's the effect of continentality. But even along the coast, not all ocean waters have the same effect. The temperature of the water itself can make a big difference. That's where ocean currents come in. So take Arica, Chile, and Rio de Janeiro, Brazil, for example. Both sit on the coast at sea level, and Arica is actually a few degrees closer to the equator, but it's about 10 to 12 degrees cooler on average. The reason is the ocean currents offshore. Arica lies along the cold Peru current, while Rio sits beside the warm Brazil current. Both affect the temperature of the air in the region. So we've seen how ocean and land shape temperature, but the atmosphere itself is also constantly moving heat and moisture around the planet. Around 30 degrees north and south, the air is sinking, part of that global circulation we studied earlier. When air sinks, it compresses and warms, and whatever moisture it was holding is now relatively little compared to its capacity. So this means it actually absorbs moisture from the surface and takes it toward the equator and poles. So that's why when we look at a satellite view of Earth, we can see a band of deserts right around this latitude, as in northern Africa and the Arabian Peninsula. So it's not a coincidence, it's a direct result of the way global circulation redistributes moisture. So atmospheric circulation doesn't just move air, it sets up these whole zones of wet and dry across the planet. So now that we've looked at each control, let's take a step back and see how they fit together. Latitude sets the baseline, so how much solar energy a place receives. Elevation cools the air as we go higher, shaping mountain and highland climates. Continentality, topography, and oceanic circulation all modify the baseline, influencing how heat and moisture are distributed near the surface. And finally, atmospheric circulation moves air, and with it, moisture. Together, these controls create the incredible variety of climates that we see on Earth. So now, let's take a look at how we classify or put those climates into groups. So this map shows the Köppen climate classification system. It's a way of grouping the climates of different regions for easier description and comparison. Each color on the map represents a different type of climate. So the system classifies climate by combining and comparing the average annual and monthly values of temperature and precipitation. And overall, climates are grouped into 5 larger types based on these values. So Group A is tropical humid. These form around the equator where a lot of warm, moist air converges. And there are 3 flavors here: Tropical rainforest directly at the equator, which is wet all year, like in some parts of Indonesia. Tropical monsoon, which gets very heavy rain in the summer and a short dry season in the winter. And then tropical savanna, which has these really distinct wet and dry seasons, like in parts of Ghana in West Africa. Group B contains the dry climates. We have arid deserts, which can be either hot or cold depending on the latitude. And then there are semi-arid steppes, which are a little less dry. So a good rule of thumb to differentiate them is that a desert will get less than 12 inches of rain in an average year, and a steppe will get a little bit more. A couple of California examples are Joshua Tree National Park in SoCal as a hot desert, and then the Altamont Pass in the East Bay as a hot steppe climate. So we see here the average monthly precipitation as the blue bars in these climographs, with Joshua Tree National Park, which gets about 7 inches of rain, compared to Altamont Pass, which gets about 16 inches, both fairly dry. Group C includes the mild mid-latitude climates, where winters stay relatively mild compared to regions farther north. One type is the humid subtropical climate, found mostly on the east coasts of continents, in the southeastern United States and eastern China, for example. These areas are hot and humid, especially in the summer, with frequent rain. So this photo from a bog wetland in Florida shows just how much moisture is available in this climate, enough to support water-loving plants like these pitcher plants. Group C also contains the Mediterranean climates, which should be familiar to most of us because this includes the Bay Area and much of the California coast. Mediterranean climates tend to form on the west coast of continents, centered around 35 degrees latitude. They both have a clear dry season in the summer, but can be distinguished between hot summer and warm summer, where the difference is the average daily mean temperature of the hottest month. So the dividing line is 71.6 degrees Fahrenheit, or 22 degrees Celsius, which makes more sense. So we can see in our climographs that San Diego, California, just barely makes the cut for a hot summer climate. The third from Group C is the marine west coast climate, where it's humid all year. So depending on the location, this humidity can mean steady precipitation throughout the year or more precipitation in winter. In either way, there are no dry months. So we can see this climate in the Pacific Northwest, like Vancouver, Canada, pictured here, and in much of Western Europe above the Mediterranean. Group D climates are the severe mid-latitudes. These only appear in the northern hemisphere, where there's more land this far from the equator. They are defined by cold winters, but we can distinguish them by how humid they are. So from about 35 to 55 degrees north, the climate is still humid, especially in the summer. And farther poleward, from about 50 to 70 degrees, it becomes much drier. And winters there are long and bitterly cold, but snowfall stays light. You can see the contrast in these climographs. The upper peninsula of Michigan has plenty of precipitation year-round, while Anchorage, Alaska is much colder and noticeably drier. Finally, Group E are the polar climates. This includes tundra and ice caps, which both have long, cold, dark winters, brief summers, and very little, if any, precipitation, mostly or entirely as snow. Tundra can be found in areas like Alaska and northern Russia, and ice caps are found on Greenland and Antarctica. Some modified Köppen systems add a sixth category, H for highlands, to separate cold, dry mountain climates from true polar ones. So my maps here use the original system. So that gray area you see in South Asia, that's the Himalayas, where Mount Everest is, and it shows up as tundra under Köppen's original rules. The last point to make, now that we've spent so long looking at climate averages, is that these are generalizations based on data. Each of the climagraphs I've shown you are based on data collected over 30 years. And this gives a big picture, like how the Bay Area has dry summers and wet winters, so it's a Mediterranean climate. But not every year will follow the average. For example, depending on your age and how long you've been in the state, you may remember the drought we had in California in the 2010s. From 2011 to 2017, a persistent anticyclone parked itself off of our coast, preventing winter storms from reaching California for like 6 years. If we plot those drought years on top of the 30-year average, you can see a clear dip in winter precipitation, that chunk missing from the usual curve. But because those years are included in the data set that defines our climate, that variability becomes part of the average itself. It's taken into account that some years are actually drier or wetter than others. And now that we've learned about climate, in our next video, we'll be talking about how climate is changing and the role that humans play in that change and how it's impacting Earth. Thank you for watching, and I'll see you next time.